Okay, so in this video we're going to use the Ka, which is the acid dissociation constant, or the equilibrium constant for a weak acid dissociation, in order to calculate the pH. So essentially where we're going with this is we need to figure out how much H plus is going to form at equilibrium, and then you take the negative log of that and you get the pH. So first thing we're going to do is sort of write out this equation here. HCN, hydrogen cyanide aqueous, is going to reach an equilibrium with the dissociated form H plus and Cn minus, both aqueous. Okay, and if we set this up in a Rice chart to take a look at what we're dealing with here, we know that our initial concentration here is 0.10 molar. We have 0 and 0. Okay, so for the change, for every hydrogen cyanide we break up, we are going to form 1 H plus and 1 Cn minus. And therefore at equilibrium we have 0.10 minus x, x, and x. Okay, so now that we have that done, we can go ahead and write out our Ka expression. And our Ka is equal to the concentration of H plus times it's going to be the concentration of Cn minus. And that is all going to be divided by the concentration of HCN at equilibrium. Alright, so going through this right now, we now know that the Ka is going to equal x times x, so x over 0.1 minus x. And that means that our Ka, which is 4.9 times 10 to the negative 10th, is equal to x squared over 0.10 minus x. Now there's two ways to solve this. The first way to do it is to simply take this, plug it into our calculator like we did with equilibrium. You can go back and look at the equilibrium videos to figure out how to do that with a TI-84. Alternately, if you look right now, this is a very small dissociation constant, 10 to the negative 10th. Anytime you're sort of 10 to the negative 5th or smaller, you can pretty much assume that so small an amount is going to go away that if you have enough concentration, like 0.10 in this case, that x is going to be so small it's not really going to change the 0.1. And therefore, that 0.1 minus x is essentially 0.1 as far as the significant figures we're going to look at matter. So we can sort of assume that away. We can just solve for it without this. Now there's a test to check whether you are allowed to do that or not, and what you simply do is you check the percent ionization. And as long as the percent ionization is less than 5%, then it's fine for you to go ahead and use that value of x that you found. So taking a look at this one right here, we're going to take 4.9 times 10 to the negative 10th, multiply it by 0.1, and then take the square root of that. And what we'll get is that x is going to come out to 7.0 times 10 to the negative 6th. Okay, if we wanted to check the percent ionization, we simply take that and divide it by 0.10. So 7 times 10 to the negative 6 divided by the 0.10 original molarity times 100. Okay, and our percent ionization there is 0.007%, which is easily small enough that we don't have to worry about this at all. Okay, so now all that's left is to calculate the pH. And since we now know the value of x, okay, which is the concentration of H plus at equilibrium, we can simply take that the pH is equal to the negative log of concentration of H plus. And in this case, that means the pH is equal to the negative log of 7.0 times 10 to the negative 6, which means it is equal to 5.15. So there we go. We have a pH of 5.15 as our final answer, and that's how you can use the Ka to calculate the pH.